Recording in progress.
Yeah, cam's on video. So let's start off. We'll not be having a break today. We'll wrap up a little early today, so not that great. Let's see, but at least let's part of it. So last thing we did was this. Great. So we saw all these different weird equations, exponential, all that stuff. But in our portion, right, we'll be limiting a study to only very specific waves and specific type of equations. Oscillating in SHM. That means the whatever source is generating this sound must be oscillating in SHM. So that is one thing. That means all our wave equations will be simple sine and cos functions. We will not see that exponential, all those weird functions, even though those are valid wave equations. So for transverse waves, again, in our study, we only have two types that we study in this. For transverse wave, we will study waves on a string. We have a separate chapter called EM waves, electromagnetic waves. There we'll study electric and magnetic fields, but in this chapter, we'll only deal with waves. And for longitudinal waves, we will study only sound waves. So in our portion, we will study only these two. So our general equation will look something of this sort. Y is equal to A sine K x plus or minus Vt plus some phi. So if you actually write this down, this will be Y minus Y mean. Again, this thing, if you write it as displacement, I'll just write it as Y only. Remember, Y is the property. So Y is equal to A sine Kx plus minus omega t plus phi. If you see the whole equation, right, it looks like SHM. If you just remove this kx, doesn't this look like SHM? So what you're actually studying is, if you put x is equal to 1, you're studying SHM for a particle which is at x is equal to 1. If you put x is equal to 10, you're studying the SHM of a particle which is at x is equal to 10. So wave equation is nothing but SHM for different particles. When you combine all those SHMs together, what you think is a wave. So this is our general equation. And the terminologies are the same. So A is your amplitude. Y is the property. For a waves on a string, Y will be the displacement of the point. For electromagnetic waves, Y will be the electric field. For sound waves, Y will be the pressure, density, displacement. So Y can be anything. K is given by 2 pi by lambda, which we call as wave number. Omega is your angular frequency, which is 2 pi f. V wave is omega by k. omega is 2 pi f and k is 2 pi by lambda. That will give you f lambda. This is what you studied in chemistry, speed of lattice frequency into wavelength. Then the plus and minus will tell you whether the wave is going right side or left side. Phi is your phase angle. And lambda is your wavelength. We will talk about that wavelength in a bit. School ka definition, wavelength is simply the distance between the crest and the troughs. There, this is our main thing. You can note down that equation at least. In books, right, they will write sometimes as omega t plus or minus kx. Both are fine. There is only a phase shift of pi, isn't it? So you can write omega t plus or minus kx. You can write kx plus minus omega t. There's not much of a difference. Meaning, if I have to show you the difference, it would look like this. If you say y is equal to a sine kx minus omega t, or if you say y is equal to a sine omega t minus kx. So if you try to plot the graph at t is equal to 0, we are plotting a yx graph. Now see, if I put t0, this will become y is equal to a sine kx. Or let's say put x0. Let's study yt graph. So meaning you're studying the displacement of the particle at the origin. If you look at this, this thing will be actually a minus sign function. Y is equal to minus a sine omega t. So if you take this x0, so y is equal to a sine omega. So not much of a difference. There is a phase shift of pi. So if you see in books, sometimes if don't get confused, just understand it as a phase shift of pi. You could have used anything. The graph starts like that. Clear with this? Because sometimes, most of the time, I will use kx plus minus omega t. But sometimes you'll see in books omega t minus kx. So don't think like it is something new. So that is there. Clear. Now let's talk about this wavelength. So we defined something called phase difference between 2 points. Now we studied phase difference in SHM. But what is phase difference between 2 points? Now again, you need to understand. So when you take this wave, let's say if you're taking a yx graph, so this is the photograph. So if you choose any point here, let's say this is point A, right? If you choose any point here, B, now see, A is simply going up and down here, getting it? A does not care about the wave. Similarly, B is going up and down. So this would be the mean position for A. This would be the mean position for B. So every point is doing its own SHM. It doesn't care about the other particle. So at this particular point, right, this will have some phase angle. So if you look at the equation of A, only if you look at A, this will be something like A sine omega t plus 5A. So if I try to write the equation, and let's say the distance between them is delta x. So y of A will be A sine kx minus omega t plus, I'll take minus for simplicity. If you take yb, the only difference will be the x coordinate is little more. So it will be k into x plus delta x. So if you look at this k delta x here, this is the extra path difference. So the difference between A and B, right? The x coordinate will be x plus delta x. So this is that additional path difference. So that k delta x is the path difference between A and B. Or extra phase difference. So phase difference between A and B will be k delta x. But we know k is nothing but 2 pi by lambda delta x. So this would be nothing but, let's say at this point, so this would be nothing but phase of A minus phase of A. I'll give an example with some numbers. So if this phase difference becomes 2 pi, we define it as wavelength. So wavelength lambda is defined as, school ka definition, the distance between two crusts and two troughs. Symbol is lambda. Minimum distance between 2 points in phase. Meaning if delta x becomes equal to lambda, means you will find one more point here. If you go here and if you look at, you will find one more point here C, or if I take one more point here somewhere B. So A is going up, you'll find this point is also going up. So this point and this point will always go together up and come together down. So that distance between those 2 points is called a wavelength. The simplest thing is to say the crusts and the troughs. But that phase difference thing is quite an important formula, right? Definitely remember this. Anyway, we are going to see this in wave optics. Let me give an example with some numbers. That's better. But are you getting now what was happening? So on the string, every point is executing its own SHM. If you look at here, A is here, above the mean position and going towards the extreme. B is below the mean and going to the left extreme. So every particle will have different phase differences. If you subtract these two phase differences, that's what we call as phase difference between 2 points. Meaning, let's say you are on the right extreme, I'm on the left extreme, then the phase difference between you and me is 180 degrees. Isn't it? Your equation will be sine omega t plus 90. My equation will be sine omega t plus 270. So let's see an example. So let's say we have a wave. So let's say this is point A. And let's say this height is root 3 a by 2. And let's say it is going up. And let's say we have a point B, which is going down. And let's say this height is a by 2. Getting it? Two different positions I have taken. So if I ask you what is the distance between these 2 points, that itself is a question. So there are 2 points like this. One is at root 3 a by 2, one is a by 2. Find the distance between them. Right now, if you look at this from SHM perspective, just look at Ega motion. This was your mean. You're here, going up, where y is equal to root 3 a by 2. Anyone remember what is the phase difference for this? So what is phase of A? With this SHM, everyone. Root 3 by 2 matlab kya? 60 degrees. It's going from 0 to extreme. So pi by 3, na? 63 degrees. 60 degrees. Similarly, if you look at B, what about B ka angle? These are proper CT level main solve questions, right? They just ask you the phase angle. You're at B and you're coming down. Anyone, what is the phase angle for this? You're at A by 2. This is what I said, remember? A by 2. A by 2 matlab 30. right? But it is coming towards the mean position, meaning if you had completed, it had been 180. So you are 30 degrees short of completing an half revolution, isn't it? So the phase angle is 150. So phase angle of A is 60. Phase angle of B is 150. So the phase between A and B is 90. Phi B minus phi A, which is 90 degrees. So this will be K delta X is equal to pi by 2. K is nothing but 2 pi by lambda. Therefore, delta X is lambda by 4. So there you can find distance between 2 points like this. So the distance between A and B is lambda by 4. Is that making sense? So if you go on like this, you'll find one more point here, C, which is also going like this, which is also at a distance of root 3a by 2. Now, if you try to measure this distance, this will come out to be exactly lambda. So that's the definition of wavelength. So A and C will always go together up, will come down together. They're always in sync. Is this making sense? What is the phase difference between 2 points? So think of like this, wave equation is nothing but infinite particles doing SHM. Is this clear? What is the phase difference between 2 points? See, every particle will have its own phase. But what is that? That is a comparison with respect to its mean position. Na? When you say phase of a particle, it's your comparison with your mean position. But when I say phase difference between 2 points, you're talking about two particles in SHM, दोनों का बीच का phase. Any doubts on this pitch? It's an important one. We are going to encounter this again in wave optics, but idea is this. So if you see this now, the whole story is actually like this. You have infinite points on a string. Okay. Now the first particle का phase angle is 0. So it will be here only at the mean. This phase angle is 10. So thoda ऊपर होगा. This thing is 20, little more. 40, right? 60, 90, then 110, let's say 120, then somewhere here, then somewhere here, then some 180 degrees. So this is 180. You're getting, forget about the wave. You just look at the particles. Next thing, 190, it will be little less. 220 here. Next thing here, 270 will be here, then here, then here, then here. Now, if you join all these particles, can you see the wave? Next moment, what will happen? Next moment, the one who is 0 will become 10. So it will go little up. The 10 becomes 20. So he will go little up. 20 becomes 30. He will go little up. The 90 becomes 110. So this guy will go up, this guy will go up, and this guy will come down. Something like, I didn't draw it properly. This guy will come down. Then this guy will come down more. This guy will come down more. So now the 170 guy will become 180. No, no. That guy will come to 0. Then here, then here, then here, then here, then here, then here. Now, if I try to join this, this is how the wave looks. So for a person who's looking at this, what will he think? The whole bump has traveled to the left, isn't it? Tell me one thing, but how is this particle moving? This particle is going only up and down, right? The particles are going only up and down. But when you see that whole string, it gives you a feeling this black color one has moved to the left side. Are you getting what is happening? So when the phase angle continuously keeps changing, this is what happens to all the particles. They change their positions. And when you connect them, you get a new sine wave. And this gives you a feeling as if the sine wave is traveling from right to left. Clear with this? So technically, that is what is happening in a wave. Great. So let's see a question on this. Let's say we have equation y is equal to 10 sine pi by 3x minus pi by 6t. Find phase difference between X is equal to 2 meters and X is equal to 7 meters. So there are two positions on a string. Find the phase difference between them. Find distance between 2 points. Whose phase difference is pi by 3 minimum. Let's get these two. First was easy. Second is a little tricky. I asked you something else. No, actually, sure, we can get it directly. Actually, I think I overthought. What is the first one? What is the delta x? Delta x will be 7 minus 2. 5 meters. So what is the phase angle? K delta x. Here, remember this was K. This was pi by 3 into 5. 5 pi by 3. What about B? Why did I think it will be different? Okay. K delta x is equal to lambda pi by 3. This is a straightforward substitution actually. This is pi by 3 delta x is equal to pi by 3. I thought of something else. Delta x is 1 meter. I thought of this. The difference in y coordinates is minimum. Find the minimum difference in y coordinates whose phase difference is pi by 3. Understood what I was asking? This is horizontal distance, na? I wanted to ask ya minus yb, the vertical distance. I mean, one is here, one is here. This vertical distance should be minimum for a pi by 3. Can you do that? What I asked you now is xa minus xb. वो तो constant रहेगा. That is always 1 meter only. But ya minus 1 will be different, na? For example, say, in a sine wave, if you take the particle here, x is equal to 0, and this will be 1 meter. But I can choose 2 points here and here such that this can be minimized, isn't it? I can make that 0 also actually, na? So that will be 0 also actually. Isn't it? Can't I find a point where both are at same difference? I should have asked something else. No, it can be 0 also. Okay, let it be. I didn't frame it properly. Next one. Y is equal to 10 cos square pi by 3x minus pi by 6. This is your y equation. This is your y coordinate. If you remember, we have done something like this in SSM. Find amplitude. Y mean. V wave. Lambda. पार्टिकल का मैक्सिमम स्पीड। Action of the particle x is equal to 2 meters at t is equal to 1 second. And the phase angle. Let's get this all. There, I give you a wave equation, you get the data. See, how do you convert this? This is y is equal to 10, 1 plus cos 2 theta by 2. This will be y minus 5 is equal to 5. Sin 90 plus theta is cos theta. That will become cos 2 pi by 3x minus pi by 3t plus pi by 3 plus 90, so 5 pi by 6. This is your y mean. Because that's your y coordinate, right? Because y is supposed to be displacement. This is your amplitude. This is your k. This is your omega. This is your phi. V wave is omega by k. Particle का maximum speed is, you can use all your SHM का results, a omega. Phase angle भी आ गया. What else you need? Lambda also you'll get it. So k is equal to 2 pi by lambda. Acceleration of the particle. How to get acceleration? Differentiate now. Acceleration is nothing but dou square y by dou t square, do partial differentiation 2 times. And then substitute x is equal to 2 and y is equal to 1. So you can also find velocity as function of time t. So velocity will be dy, dou y by dt. Be careful, you have to differentiate with partial differentiation. Dou y by dou t. So this guy will become minus 5 pi by 3 sine. X will not get affected. That pi by 3t plus 5 pi by 6. This is your velocity. Acceleration, again differentiate this dou v by dou t. This pi square by 9. This will become cos actually. This will again sine 2 pi by 3x minus pi by 3t plus 5 pi by 6. But if you just want acceleration, you can do even something better. A is equal to minus omega square y, isn't it? Because it's SHM. I could have done that also. You would have got it either way. Clear with this? This y should be displacement. So the general equation will be y minus y mean. Hmm. So if at all they ask you sometimes, na, at this position, at this time, differentiate, partial differentiation, you can use your regular kinematics. All clear with this? This is one. I'll give you an equation, you'll get me the data. The other way around. I'll give you the data, you get me the equation. Let's say this is a yx graph. Basically, it's a snapshot of a wave on a string. At t is equal to 0. This is 2 meters. Basically, this to this. There is a point P here which is going up. Vp is 4 meter per second. And if you draw a tangent here, this point is making 60 degrees. And this height is a by 2. V particle come maximum speed is 10 meter per second. This much information you have. So find the wave equation. Just to keep it more clear, this is what I'm asking. Let's say y main is 0. So y is equal to a sine kx plus minus omega t plus phi. That means I want you to find amplitude, I want you to find k, I want you to find whether it is plus or minus in the middle, I want you to find omega and phi. If you can find these 5 values, your job's done. So we are taking y mean is 0. So you have to find amplitude, k, omega, plus and minus, sine, and phi. So that's it. This is all the data you have. You have a picture of a string at t0. Particle ka maximum speed is 10 meter per second. That's it. Get them. This would be a pretty good advanced more than one choice question. If I just ask you individual pieces, I can make 3 or 4 mains questions out of it. So try. I'll give 2 or 3 minutes. Just give it a try. Did you figure out any bits and pieces of it? Lambda is easy to find. Try. I'll give it a minute more. Oh, let's see. Someone got something. Negative sign for sure. Yeah. First thing. This thing is nothing but lambda by 2. Half of the wavelength. That is clear. That is half of the wave. So lambda by 2 is equal to 2 meters. From here we got lambda is equal to 4. K is 2 pi by lambda. K aa gaya. Now, then we have to use this information, which I'm pretty sure you forgot. Vp is equal to minus V wave dou V by dou x. Yeah, there is a relation between particle speed and wave speed. That's why Vp is given. So that is 4 minus V wave dou V by dou x is tan 120. You should take always with the positive x axis. So we get V wave is equal to plus 4 by root 3. The plus indicates it's a right traveling wave. Now understand, when I say plus I cap means it's going right side. So in the equation, you'll get a minus sign. Clear? So this should be in the form of kx minus omega t times. You got V wave. Once you got V wave is omega by k. From here you got omega also. And amplitude is what? Vp max is nothing but a omega. From here you got amplitude also. You got everything except phase angle. How will we find phi? That's where most people get trapped. Most people figure out till here. Most people look at a by 2 and they're at 30. It's not 30. Just because you're at a by 2 doesn't mean it is 30. That's where the trap is. Let's see. This is a catch. Already got tan 120. Slope na record. This is 60 na. So this is 120, right? For the tangent. Na? Slope of a tangent. See here, the thing you have to be careful. This was the wave at t is equal to 0. Great. How is the wave traveling? Wave is traveling towards the right. Means next moment, how will this bump become? The bump will actually become like this. This is after time till let's say 0.01 second. Now, did you see what happened to A? A traveled from where to where? A used to be here, that point. It has come down, na? That point is traveling downward, isn't it? Now you tell me, in SHM, if the particle is at A by 2 and if it is coming downward, what is the phase angle? Means from the mean position you went up and then you're coming back and you're at A by 2. So the phase angle is 5 pi by 6. Is that making sense, everyone? So you have to check, just because you're at A by 2 doesn't mean it is 30. Is it going away from mean or coming towards the mean? वो भी check करना था. Clear this. So based on this, let me ask you another question. All clear with this? It's a good one. Matlab, you can see all the data points. Now you can put all there, you'll get the answer. Let's say this is a y-x graph. There are 4 points here: A, B, C, and D. I didn't draw it properly, but here. And the wave is traveling towards the right. Case 1, this is a transverse wave, wave on a string. Case 2, this is the y-x graph of a, basically this is a snapshot. You took a photograph. This is a y-x graph of a longitudinal wave. Sound wave, basically. Again, what's the difference in both of them? In both the cases, see, x is this. So in the first case, the particles are going up and down. So this is your y. In the second case, the particles are going front and back. So this is y. Again, remember, y is not the y coordinate. Y is the displacement from the mean position, isn't it? In transverse wave, the displacement is along the y-axis. In longitudinal wave, the displacement is along the x-axis. So be careful. Most people see that y and think it is a y coordinate. Y is not the y coordinate, it is a property. Now the question would be this. This is a good mains level question. In which direction does ABCD move? Options will be up, down, right, left. Now, here I explained all this story, and they won't tell all this story there. They'll simply say this is the y-x graph of longitudinal wave and done. Now you need to figure out all that. So in which direction does A, B, C, D move? Options will be up, down, right, left. 2 questions, 4 points. Get them both. It's a good mains level question. Someone is not clear what I'm asking, please ask me. Let's see. Most of you got it, I guess. Now see, one easiest way to do is completely go mathematical. At this point, if you look at the slope, positive, negative, negative, and positive. So we can use Vp is equal to minus V wave into slope. Here V wave is already positive. That means it is opposite to the slope. So case 1, VA is negative, means it is going down. VB is positive, it is going up. VC is also positive, going up. Now in case 2, the same stuff. The only difference is this. Now it will not be up, down. Negative means it is going left, right, right, and left. That's the difference, isn't it? In a longitudinal wave, plus means you're going in the direction of the wave, right side. Negative means it's going to the left side. Is that clear, everyone? So you have to be careful whether you're talking about a transverse wave or a longitudinal wave. Y is not always the y coordinate. Clear this? But if it is only a transverse wave, there is a little easier one. Think about it. If it is a transverse wave, next moment, how will this pulse go? From here, it will go like this, na? That means what happened to this point A? A has come down, B has gone up, C has gone up, and D has gone down, isn't it? You can just move the pulse a little forward, and then you see how these points, because A will always go up and down only. So A has gone from the green one to the red one, once it must have come down. So that's a non-mathematical way of doing. You can see and tell, oh, this is what happened. You can actually use the same logic for longitudinal wave also. So A ka displacement has decreased. Matlab it is going towards the mean position, means it is going towards left, isn't it? The only thing you have to be aware, are you talking about a longitudinal or a transverse wave? That's where people goof up. So mostly exam they'll give you longitudinal wave and they'll ask you. But people will think this is a wave on a string and they'll write the answers up and down. That is how they can trap you. But it's a good one. Clear with this? That is one. Now, next thing, like this is all about the wave equation and everything. Next thing, like I said, we will be studying waves on a string for transverse and sound waves for longitudinal. So first thing we will deal with waves on a string, and then we'll go for sound waves. Most of the concepts will feel similar, but in both the longitudinal and transverse, some differences. So the first thing is a waves on a string. So the first thing that we'll study is a wave speed. Again, we'll not be doing the derivation. It's not really that important. At least wave speed derivation is not important. So if you have a string and if you generate a pulse on a string, the formula for V wave is given by root over T by mu. T is the tension in the string. So more tension, the faster it will go. Mu is your linear density. Unfortunately, we can't use lambda because we're already using lambda for wavelength. Lack of symbols. So mu is your linear density kg per meter. So it's the same thing lambda which we used in center of mass and everywhere. This is your main formula there, V wave. Again, if you look at the formula, you can clearly see something. Means as long as you know how to find tension, you can get the wave speed, isn't it? So the whole wave speed is based on again finding tension, just like elasticity. But there's one thing, this is a wave speed with respect to the string. This is not in the ground frame. That means, let's say if you have a truck and it's a truck itself is going with 20 meters per second. And let's say inside the truck you kept a string like this with a pulse. And let's say this pulse itself is traveling with 5 meters per second. Basically, this is your root over t by mu. So if someone asks you what is the velocity of the wave with respect to the ground, it's not 5. That will be 20 plus 5. 25 meter per second. So the 5 meter per second is with respect to the string. Clear with this. If the string itself is moving, then the string speed also will add up. So if you know how to find the tension, the job's done. You can just put it there and get the answer. The derivation is because there is one easy definite derivation, but that's a lot of approximations. There's very complex derivation which we don't need. So overall, it's a waste of time. So let's not worry about it. The one with the easy one is too much approximation, and the other one is too complex. Let's see some questions on this. That's it. There's only one formula for wave speed. This is for a string. This is a wave speed on a string. For sound, there is another formula. If it is not a string, then there's another formula. So luckily, we don't have all that stuff. We have only wave speed on a string and a sound wave bus. Let's see some questions. Again, you will see most of the questions will look similar, whatever you have done in elasticity. So we got a rod here, mass m, length L. We got a block here, mass m, a distance of L by 3. This is mu and this is mu. You have generated a wave on this. You have generated a wave on this. This is V2 and this is V1. So wave pulses are generated on the supporting strings. Remember this question? We saw this in rotational mechanics, equilibrium are generated on the supporting strings. Find V1 by V2. So you generated, basically when you say waves generated nothing, you just like a guitar ka string, you plugged the string and left it. The pulse started traveling. Get this, I'll give you a minute. It's an easy one. Again, there's only one formula. V is equal to root T by mu. Both the strings are identical, so mu and mu, but tensions will get messed up. let's see, 13 by 11, root 2, root 7 by 5. Step 1, draw the FBD. What are the forces? T1, T2, your own weight mg. This is mg. T1 plus T2 will be 2 mg. Then take torque about any one corner. I'll take torque about A. That would be T1 ka torque will be 0 torque due to T1, torque due to mg rod, torque due to mg block, torque due to T2 is 0. So this is 0, this is mgl by 2 minus k cap. This is mgl by 3 minus k cap plus T2 into L. K cap. Is 0. From here, you will get T2 is equal to 5 mg by 6. T1 will be 7 mg by 6. And we know wave speed is equal to root over T by mu, proportional to root T. V1 by V2 is equal to root 7 by 5. See where it went wrong? Just an FBD torque equation and force equation. We have done this the third time. We have seen this thing in elasticity also. Clear? Next thing. Ring of mass M, radius R. This is rotating with omega. It's a rope. Maybe you can say rubber cord or something. On this, you generated a wave pulse. Now, this wave can go in this direction or it can go in this direction. We don't know. Find the wave speed with respect to the ground. Basically, there are two answers. Because that formula root T by mu will only give you wave speed with respect to the rotating ring. But ring itself is moving. So find the wave speed of that, find the wave pulse with respect to the ground. Mm. What are you guys finding? Let's first find the tension. You know the drill. Take a small piece, d theta, you write all that story there. So this will be tension, this will be tension. D theta by 2, d theta by 2. This will be dm omega square r. This angle will be d theta by 2. You can check it out with this in circular motion. Okay, multiple times. 2t sine d theta by 2 will be dm omega square r. Small angles, sine theta becomes theta. dm becomes mass by total length 2 pi r into r d theta into omega square r. You get tension is equal to m omega square r by 2 pi. So V wave will be root over T by mu, which is actually m omega square r by 2 pi, and this is m by 2 pi r. You actually get a good result, omega r. Now there are two possibilities. One possibility, both are going in the same direction. It will be r omega plus r omega to r omega. This is the same direction. If you go in the opposite direction, it will be zero. So for a person outside on the ground, it will feel like the bump is at rest. Meaning what you will see is simply the string will be like this. You will see a bump. It will be just there. The ring is rotating. You will just see a bump there. Yeah. Hmm. M won't come. It will cancel out. See where it went wrong. Next one. Any doubts on this? We have a rope hanging from the ceiling. This is x is equal to 0. This is x is equal to L. The linear density mu is equal to mu naught x power n. Mu naught is constant. N is a number. N is not equal to -1. It can be any other number. You have your regular gravity as it is. So you generated one pulse here. Let's call it wave 2. Basically, you pluck the string. See, that's the meaning of generating a pulse. And you generate a pulse here also, which will go up wave 1. So first question, find the time taken. Or let me ask you like this. Find the acceleration of the pulses. Find time taken for wave 1 to reach the ceiling. If I put n is equal to 0, that becomes a standard mains level question. Basically, mu becomes constant. Find time when the pulses meet. Find time and the position where pulses meet. I'll just ask position. Let's get this. So here the catch is tension in the string is not constant. As you go up, tension increases. So it's a variable tension. Let's start from there. Try. I'll give 3-4 minutes. Once you got the first part, actually everything will come back to back. Let's see. Someone got by 2 G. The dimensions are not matching, right? Pushkar? नहीं सच. I think you guys are messing up something. G by 2. ये तो रट्टा मार लिया कहीं से result. Roja, I think you got it. Let's see. I know mu naught x तो it's the standard result. People remember. X power n तो suddenly people are thinking. क्या करना है? So you want to find the tension? So if you take it a distance x from here, so you want to find tension here. So take a small piece anywhere, dx. So you want to get the tension here. So tension T will be integral dmg, isn't it? Just add all the weights from 0 to x. What is dm? Mu naught x power n dx. That's your dm from 0 to x. So tension will be mu naught g x power n plus 1 by n plus 1. This is your tension. So what's your wave speed? Root over t by mu. This is mu naught g x power n plus 1 by n plus 1, and mu is nothing but mu naught x power n. So you get v wave is equal to root over mu naught g by n plus 1 into x. You want acceleration, I can do a is equal to dv by dx. That is one way to do, but there is something even better. If I square this on both the sides, I can write this thing as v square minus 0 square is 2 by g by 2 into n plus 1 into x. Doesn't this look like v square minus u square is equal to 2ax? Isn't it? Actually, when you do v dv by dx, constant ही आएगा. This looks like your SHM का third equation. So we get acceleration a is equal to g by 2n plus 1. There. That's a pretty good result. मतलब you get a constant acceleration. If you put n is equal to 0, it becomes a uniform rope. You get g by 2. That's your standard result. So there, actually, now we know that means both the pulses have same acceleration upward, but wave 1 ka initial speed is 0, wave 2 ka initial speed is not 0, isn't it? Wave 2 ka initial speed is not 0 because if you see the wave speed, if you put x is equal to L, the wave speed is not 0. If you put x is equal to 0, wave speed is 0. So indirectly what you have created is two waves. So this is wave 2, whose acceleration is root over. The speed is root over gl by n plus 1. This is wave 1, whose initial speed u is 0. And this guy has an acceleration a, which is g by 2 into n plus 1. So this is accelerating, and this guy is decelerating. This thing kind of became like a two stones thrown from a building type problem, isn't it? And the question is, where will the two stones meet? So these two pulses will meet somewhere here. I can use relative velocity. So V relative is u only. What is A relative? A relative is 0. So what is time? L by u. That is when they meet. When will they meet? So if I take this distance to be x, I can just use this thing in the ground trim. X is equal to ut plus half at square. For the wave 1, u is 0. So half a time is L square by u square. This is where they meet. Easy. And when will this wave one reach the ceiling? That is also easy, no? Wave one reaches ceiling. Now, once you got the acceleration, you get everything. So wave one reaches the ceiling. Again, I'll use the same formula. S is equal to ut plus half at square. But this time, S ka place mein L will come because you have to travel the whole thing. U is 0 and half into A into T square. T is equal to root over 2L by A. You get everything. Once you figured out A is constant, it simply becomes a kinematics. You can play around with this. This acceleration is including gravity. Na, Purja. Basically, it's not a particle, na, right? It's a wave, it's a disturbance, na.
The tension will cancel out the gravity.
Basically, gravity, because of gravity, tension came.
Huh.
Hmm. Got it? It's like this thing when I'm shouting, na, my sound doesn't go in a parabola. Gravity doesn't act on sound. It's like disturbance, you're getting it. So that way. Any doubts on this thing? So the main thing is getting the tension as function of x. Once you got that, once you figure out the acceleration, everything is straightforward. Any doubts on this? Clear? Let's see one more. Let's say we have a very long rope, infinity. This point z is equal to 0. So mu of 0 is mu naught. This is your linear density at the top. Means at the topmost point, the density is mu naught. Gravity is there. Assume gravity is constant throughout. Then the string is a little weird. We observed when you generated a wave pulse. Think about it. If you have a wave pulse, as you have a long string, the tension should keep changing. If tension is changing, wave speed will change. Z is the distance from the top. So we observe the wave speed remains constant. So this pulse is traveling up with a constant speed v. We observe the wave speed is constant value, which is v wave is equal to v. Find mu as function of z. So this happens for a particular function of a linear density. What is their function? Linear density as function of z. It could be anything, something like 1 plus z square, 1 by 1 plus z square, sine z, any weird function. So how is mu changing as function of z? Any guesses what should the function look like? Unfortunately, you won't be able to guess in the exam because there'll be two options you'll get stuck. But right, Puraja. So when you say v constant, now this is what I think. Root over t by mu. We know tension will change with height. Think, take for a minute. I'll tell you something. If I tell you that, it's like revealing the whole thing. You put a fight for 1 or 2 minutes. Aditya. when you see this thing now, I'll think like this thing. Matlab, tension I know must be something like mu into dx into g. And you're saying wave speed is root over tension by mu. Matlab, it'll be integral mu dxg by integral mu. And you're saying this is constant. So think about it. That means when you integrate something, you should get that mu back again. That mu and this mu will cancel. That's why you're getting a constant now. So which function, when you integrate, you get the same function back? You're getting the thing? When you integrate the function, it should give you something that should cancel with mu in the denominator. Matlab, when you integrate mu, I want mu to come back again. Exponentials, isn't it? Those are the only functions which will give you the same function back. Itna to clear tha. Matlab, this thing, whatever it is, must be an exponential. Now, that what is that e power something constant and all, we need to figure out that. So in this, first thing we need to figure out is this. It's z tending to infinity. So mu of infinity must be 0. Simple. String is long. Other than this, if it is not 0, if you have an infinite string, tension will not be infinity. It will not be finite value, it'll go to infinity. Since the string is long, mu should keep decreasing. And we already had a guess it's an exponential. So e power minus infinity must be 0. Now again, we still don't know what is that function, but it's not so clear that it should decrease. Else tension would not be finite. And v is equal to t by mu is constant. Now at topmost point, so at z is equal to 0, we have v is equal to root over tension by this is mu naught. So if you see, tension will be v square into mu naught. This is the tension at the topmost point. This is a finite value. That means when you add all this weight, you should get a finite. So whatever that function that you're integrating, it should tend to 0 at infinity. Clear till here? Next thing. This is more of a max question actually. So this string is there. So let's say you want to find tension somewhere here. So if you take a small piece here, dz, the tension T will be integral mu of z dz into g. Values will go from z to infinity, isn't it? You should integrate everything from z till infinity. Then you'll get the tension there. Because the tension is because of the weight below the string, right? The tension is because of this part of the string. That is your tension there. So now, and we also know from the formula, tension is nothing but T is equal to root over V by mu. So yeah, right. V is equal to root over T by mu. So we have tension is equal to mu into V square. So substitute here. So mu into V square is equal to integral mu dz z to infinity. V is a constant. Differentiate on both sides. I hope you know how to differentiate an integral. Learn it in max. So if you have a function f of x dx, Leibniz rule. Yeah, a to b d by dx. This becomes f of b, then differentiate db by dx minus f of a, then differentiate dA by dx. I hope you must have learned it. So I'll do the same thing stuff here. V square is anyway constant, so V square d mu, this guy will become mu of infinity. So I can actually write it as mu of b, then dB by dz, and then I'll say b tends to infinity. But we already proved this term is 0 because differentiating infinity doesn't make sense. This tends to 0, so that whole term goes off. So you end up with v square d mu is equal to minus mu. I think I forgot a g somewhere. There is a g also. Bring it this side. और कुछ तो missing था. Forgot. This is d mu by dz. Then you're done actually. V square by g d mu by mu is equal to minus g by v square dz. Integrate. This will go from 0 to mu naught to that the next page. This will go from 0 to z. This will go from mu naught to mu. Ln mu by mu naught is equal to minus gz by v square. Therefore, mu is equal to mu naught into e power minus zz by v square. There. That's your relation between mu as a function of z. As we guessed, it was an exponential. Clear with the steps? So that's how you get this thing. The main thing is how to differentiate that. Clear with this? This is how they can frame questions also, gives on a string. Any doubts on this part? Yeah. So there. With that, I think we'll wrap up for the day. I'm not that great. I think I'm exhausted already. So we'll continue on Friday from here. Next part, we're going to see something called, energy in a wave and all that stuff, principle of superposition and all. And then that next class, we'll see something called stationary waves. So the next two classes are important. So this is a wave speed. There's nothing more. As long as you know that formula, you can keep playing if you know how to find tension and stuff. Okay, with that, we'll wrap up for the day. So anyone has any doubts, please stay back and ask. If you have more doubts, we'll see later on. But if you have 3-4 doubts, do ask, finish it off today.